Welcome back. In the previous videos, we walked through some of the important navigation aspects of working in Discovery Live, the important things for students to know and what they can safely ignore. We then set up a template for this bracket project, and in the last video, we learned some tricks for filling it in with nice cylinders here and closing any gaps that might show up and making sure it's all one object. In this video, we'll walk through the important steps of having students actually create a stress analysis or get a stress solution for this bracket to see what kind of stresses might be present in it under a particular load case. To get things started, I just mentioned making sure everything is connected is always a good idea if it's all supposed to be part of one bracket here. So students actually fabricate these in my workshop, and it is one object. So I'm going to make sure that I select everything that's on the screen here. I could just do Control A on the keyboard as well, and then use that combine tool. So if any of the brackets were actually just touching one of the cylinders but not part of the design, I just made sure that it's all grouped together right now. Next, I'm going to select everything again and then ask it to create a solution. So it'll do it for the shapes that I've selected here. If I only wanted to look at a small portion, I could create a solution for that small portion, but here I want to have everything. So creating a solution, you've got some standard tools here, including modal and fluid and thermal. The structural one is right here in the middle with the gear icon. And it's a good starting point here if you select the material that it's most likely resembling. And for my rebar project, I have students start with structural steel. We'll look at how to adjust some of the properties of this to make it perhaps match the actual material you have a little bit better. All right, we'll go ahead and create that. Nothing exciting happens except getting a few more boxes on the screen here. The reason for that is every solution, regardless of the type, needs a few boundary conditions defined. For a stress analysis here, we need to know what's actually being held in space so that it can't move, and then where's the force. Without those two things, it can't give us any meaningful information back. So I'll first fix the mounting brackets. If I kind of pivot here so I can take a look at the wall side, if I click on one of these faces, it now gives me a slightly different contextual menu here when we're in the select tool. And on the left hand side are some of the things that we're most likely to do. The top one that was there by default is the new fixed support. So that's what I want to do to that face there, is make it a fixed support. And if we look at it, it's kind of hiding under the origin there. It puts a little icon on that face. It'll be easier to see it down here, which indicates that it's actually a fixed face now in the simulation. And we can even see that when we pivot away, it lets us know where that is. The second thing that we needed was to tell it where the force is, both magnitude and direction, since it's a vector. Part of the reason that we put this object out here was so we'd have a nice face to put the force on. I'm first going to demonstrate why this was important. So if I just clicked near the end and said I want my force to be here, right behind this hook, maybe this is just something to keep things from sliding off. So a student usually will click here and select a new force. And we see what happens. It tries to put that force halfway between the two ends because that's the, technically the center of this cylindrical face. And that's not what we want. So I'm going to escape from there. So if I click on this cylindrical face here, it's going to keep that force right in the center of this circle, and I can make sure that it's normal to the surface by default, so it's going to be going straight down. So new force there. For my students, I tell them to use 186 newtons because that's the value that we're using to actually test their fabricated final products. It's the weight of a 5-gallon bucket full of water. Default units here are newtons, so you don't have to explicitly put the in on there, but if you do, it's not going to hurt anything. Once I hit enter, it commits that. We now have all the appropriate boundary conditions set up, but we don't see any color yet. That's because we haven't started the solution down here. So after creating the solution, we've got some new buttons. So let's just take a quick look at each. Pressing play, we'll have the hard math happen in the background for us, and it conducts that finite element analysis. Now it's actually color-coded our design to show us exactly where it's going to experience a very high value of stress and places where it's going to experience relatively low values of stress. And those correspond to the colors on the scale over here. Top value will be whatever the maximum stress value was in the entire design. and the units here are megapascals, measured in von Mises stresses. And that all will take quite a bit of explaining with students. But if they really focus on stress being a force per area, same units as pressure, newtons per square meter, and then a refresher on metric prefixes is always a good idea. So it's not only 244, it's actually 244 million newtons per square meter is the expected stress in this area. The force itself, if they want to adjust this value, they can easily click on it and change that number there. But if they want to change the direction as well, perhaps the face was actually on the outside here, they can still have it going downwards if they open up this contextual menu and adjust the values of x, y, and z. Here we see it's entirely in the positive x direction, which corresponds to the coordinate system definitions that we began with. If you pause the simulation and just want to make changes without the GPU of the computer working really hard to update your finite element analysis every time you make a change, you can turn it off and just refresh it manually using this refresh button. Other options here, we've got the color results. You can turn that on and off. Sometimes when students are going in to make design changes, it's often difficult for them to find their guidelines and faces when the color is overlaying it. So letting them know that they can stay in the solution but kind of hide that. You can also do a cross section. So this defines what's happening kind of internally. They can see whether their design is strong or weak just on the surface or deep inside. So here we see that high concentration of stress is mostly near the surface in our design. Lastly, the last option here shows deflection, and it will actually run a little animation if you have this playing, giving an indication of how the beam is going to deflect under that applied force. Notice the colors changed what they're representing. It's no longer von Mises stresses in pascals, but deformation in millimeters, red being the greatest deformation from the original position. So about 4.5 millimeters of displacement here. Greatly exaggerated in the animation just so we can see it. And if you wanted to do true deformation, you can actually have it scaled down. The last couple of things I wanted to show had to do with adjusting some of the values of our material so that these numbers are as accurate as possible. By default, we selected structural steel as being the material that it's using to actually calculate these values numerically. If we wanted to have that be closer to something that we're using in lab, we can actually go over to the solution menu here and right-click on structural steel to open up the material library. Here's the definition of all the materials that we could choose from, and conveniently at the bottom it shows us in our solution what we're using. For a analysis like the one that we're doing, things such as thermal expansion and thermal conductivity don't matter so much, but things like density and Young's modulus might. Young's modulus in particular has to do with how elastic the material is, how far you can bend it before it's permanently deflected, before it passes that yield point and deforms ductily. So this value here is a unique way of expressing scientific notation that may be confusing for students. In math class, they usually don't see the E value, they see times 10 to the power of whatever. So be sure to explain this type of scientific notation so that they can translate between what they've seen in math classes and what they see here and what they see on their calculator printout. I've had students determine this value experimentally in lab for rebar using a method of deflecting it as like a cantilevered beam, and they usually get values that are quite a bit less, well, not quite a bit, but a little bit smaller, like 1.7 or 1.8 gigapascals. The number, once it's entered, you actually have to, you can't like hit OK, you have to hit enter on the keyboard first, and then you can hit OK. And as soon as I start running this simulation again, you're going to see that the values on my scale are going to change. Not tremendously, but a little bit. So that's more accurate to the materials that we were actually using. Yeah, so one of the last applications I have students do here is to try to maximize the like optimize the design by using as little material as possible while still maintaining a defined factor of safety. Factor of safety is the ratio between the maximum force they expect, and the yield strength of the material. For steel, that's about 250 gigapascals. So as long as this maximum value falls, under about a third of the yield strength, then they can kind of check off their design as being good. Since we're so far away from that, we have some optimization here. We could perhaps make this beam even a little bit steeper, using less rebar and seeing if we can design that. All right, hopefully that's enough to get you started on a few things with your students. In another video, I'm going to show a few things about how to approach the design of the bracket differently, not using cylinders, which has some benefits of keeping things a little bit simpler in terms of joining up any gaps or overlaps.